In this lesson, we continue the discussion of the most important distributions that we find in probability. Let me recall that we are still dealing with discrete random variables, and the next distribution that we consider is the so-called Poisson distribution. This distribution has a lot of applications. In particular, it can be used to model a phenomenon in which, for small time intervals, the probability of an occurrence is proportional to the length of waiting time. Interesting and concrete examples are given by a bus which arrives at a stop, a customer who enters in a shop, a photon that is captured by a telescope, a radioactive sample which decays, and many others. But we find also applications of the Poisson distribution to model the distribution of fishes in a lake, or the number of stars in a unit of space, and so on. All this to say that the Poisson distribution is one that we encounter very frequently in probability. Funny story, the name of the distribution comes from the French mathematician Simon Denis Poisson, who published this in 1837 without knowing that another French mathematician, Demoivre, discussed it more than 100 years before. The Poisson distribution comes equipped with one parameter, in general called lambda, which is a real parameter strictly greater than 0, and it is sometimes called the intensity. A random variable x, taking values in the non-negative integers, is said to have a Poisson lambda distribution if its probability mass function is given by this formula here. As you can see, we have the exponential of minus lambda times lambda to the power x divided by the factorial of x. Recall that the factorial of 0 is 1, and so the formula is well defined. The Poisson distribution has a great peculiarity, that is, the expectation value and the variance are given by the same value, which is exactly lambda. Let's check this fact for the expectation value, and the proof for the variance is very similar, so you can try to repeat it. By definition, to compute the expectation value, we have to write the series, in this case because x can grow up to infinity, of x times the probability mass function. However, the first term, if we start with 0, is 0, because here we have to replace 0 here and here, and we have 0 times something that is not infinite, and so we have 0. So we can rewrite the expectation value writing the sum that starts with 1, and then we have x times the probability mass function. If we rewrite the factorial of x as x times the factorial of x minus 1, then we see that we can erase x and we remain with this expression that can be written as lambda times the exponential of minus lambda outside the sum because it doesn't depend on x times this series here. Now let's remember a general fact regarding series. Imagine that you have this series here that starts at n0 and the argument is a function of n. Then it is possible to show that this series is exactly the same as the series written here, which is obtained by subtracting and adding a fixed integer here and here respectively. We can use this fact to rewrite this series. If we subtract 1 at the index of the series, then we have to add 1 here. This is what I wrote. And as you can see, this allows us to restart the series at 0, as it is written here, at the price of adding 1 here and 1 here. But this is very welcome, because then we can erase 1 and minus 1, and we remain just with this simple expression. Now, in the course of calculus, we prove that this series is precisely what defines the exponential of lambda. And so we have lambda times the exponential of minus lambda times the exponential of lambda, we can erase these exponentials and we remain just with lambda. Let's immediately use the Poisson distribution in a concrete and nice example. We deal with the application of the Poisson distribution to waiting for occurrence. Consider a telephone operator who, on average, handles 5 calls every 3 minutes. We want to know two things. What's the probability that there will be no calls in the next minute? And what's the probability that the telephone operator will receive at least 2 calls in the next minute? To answer this question, we define the discrete random variable x, that is the number of calls in a minute. A minute is a relatively short amount of time, and so we can assume that x follows a Poisson distribution. We can know the intensity lambda of the Poisson distribution by the fact that, on average, the telephone operator handles 5 calls every 3 minutes. The average or mean is the expectation value, and so we have that the expectation value of this random variable is 3/5. Notice that this is correct because we are assuming a minute as the unit of measurement. So the probability to receive 0 calls in the next minute, that is the probability that x equals 0, under these assumptions is given by the Poisson distribution with 0 here and here, and with 5 divided by 3 here and here. Why that? Well, because we have proven before that the expectation value is precisely lambda. The factorial of 0 gives 1, the 0th power gives 1, and so we remain with the exponential of minus 5 divided by 3, which is roughly 0.19, that is 19%. To resume, for a telephone operator who on average handles 5 calls every 3 minutes, the probability of being left in peace for 1 minute is only 19%. To handle the second question, we need first this remark here, that is, the probability to receive 0 calls in the next minute, plus the probability to receive 1 call in the next minute, plus the probability to receive 2 or more calls in the next minute, must give rise to 1. So we write the probability to receive 2 or more calls in the next minute as 1 minus the probability of receiving no calls minus the probability of receiving just 1 call. That is 1 minus the value that we computed before, minus this value here, which, as you can see, is obtained by introducing 1 in the Poisson distribution formula. If you do the math, you obtain around 0.5, that is 50%. Keep in mind this strategy because it is of course much more intelligent than writing this series here starting from 2 in order to compute the probability. Regarding the possibility to perform calculations of probabilities using the Poisson distribution, we have this theorem here, which says that we can relate the probability that the random variable takes the value x and takes the value x minus 1 through this simple factor here. If we apply this formula using lambda equals 5 divided by 3, we can confirm the results that we have obtained before. In fact, if here we introduce 1, then also here we have to introduce 1, and here we have to introduce 1 minus 1, which is 0. The first computation that we performed before showed us that this probability was the exponential of minus 5 divided by 3. And so, using this formula, we have that the probability that the telephone operator will receive 1 call in the next minute is 5 divided by 3 multiplied by this exponential, which confirms exactly what we have found before. The proof of this relation is actually very easy. In fact, it is sufficient to write the Poisson distribution, then to separate the factorial as x times x minus 1 factorial at the denominator. Instead, at the numerator, we can decompose lambda to the power x as lambda times lambda to the power x minus 1. Rearranging the factors, we have lambda divided by x multiplied by the Poisson distribution related to x minus 1, which gives precisely the formula that we wanted to prove. The last discrete distribution that we deal with is the so-called geometric distribution. In order to introduce it, let's recall that the binomial distribution counts the episodes of success in a fixed number of Bernoulli trials. Let me also recall that a Bernoulli trial is an experiment with two and only two possible outcomes, success and failure. In the geometric distribution, the interest is shifted to the number of Bernoulli trials required until we get a success. So it shouldn't come as a surprise that the random variable that we consider here is x, defined as the trial at which the first success occurs. By definition, the random variable x can occur only if there are no successes in the first x minus 1 trials and a success on the x trial. But the probability of 0 successes in x minus 1 trial is given by this binomial probability. That is, the binomial coefficient x minus 1, 0, the probability of success elevated to 0, and the probability of failure, 1 minus p, elevated to x minus 1. The first two factors are 1, and so we remain with 1 minus p elevated to x minus 1. By definition, at the trial x, we have success with probability p. So, the probability mass function of a random variable which represents success at the x trial and failure for all the previous x minus 1 trials must be given by the product of p and 1 minus p elevated to x minus 1. This is called the geometric distribution, or in less rigorous mathematical terms, the weighting for success distribution. The reason for the name geometric at this point is rather mysterious. Actually, we are going to see that in order to prove that the sum of p of x as x varies from 1 to infinite gives 1, as it should be, relies on the so-called geometric series, which is this one here. Let's do a little manipulation. We write this series starting from x equals n, and then we subtract n here, and so, as we have said before, we have to add n here. This splits in q to the power n times q to the power x. Q to the power n can be taken off the sum because it doesn't depend on x. There it is. And then we can use the formula for the sum of the geometric series that starts at 0. To resume, we obtain that the geometric series when x starts at n has this sum here. Let's now use this result in order to show that if we perform the sum of these probabilities from 1 to infinite, we obtain 1. Why do we start from 1? Well, because, as we have said before, in the geometric distribution, we count how many Bernoulli trials we require to get success. And so a 0 trial doesn't mean anything. And so we start counting from the first Bernoulli trial. Okay, so let's take these expressions and sum them starting from 1. The first thing that we notice is that p doesn't depend on x, and so we can put it outside the sum. Then we can use immediately the result that I showed before, this one here, or we can perform again the same manipulation using in particular 1. In any case, we obtain this formula, which is p divided by 1 minus 1 minus p, and if you do the math, you obtain p divided by p, that is 1. Regarding the expectation value and the variance of the geometric distribution, after some calculations, which are quite technical, we arrive to these expressions. The expectation value is 1 minus p divided by p, and the variance is 1 minus p divided p squared. Let's immediately discuss a very practical example that is related to the lifetime of devices. Suppose we have a light bulb which has the probability of failing, in the sense that its tungsten filament will break, of 0.001 each day of use. We want to know what is the probability that our light bulb will last at least 30 days. Since we want x to be strictly greater than 30, we start our series with small x equals 31. Then we introduce this probability here and here. We take this number out of the series because it doesn't depend on x. Then we perform the usual manipulation in order to have the geometric series as it should be. That is with the power x here. Then we use the formula for the geometric series that starts at n that we have obtained before. And doing the math, we obtain 0.97, that is 97% that our light bulb will function for at least 1 month. With the analysis of the geometric distribution, we have finished the discussion of discrete distributions. Now it's the time to pass to the continuous ones. Similarly to what we have seen for discrete random variables, the easiest continuous distribution is the uniform one. Given a real interval AB, the uniform distribution is given by this formula here. That is, f of x is equal to the fraction 1 over b minus a when x belongs to the interval AB and 0 otherwise. This value is a constant. For this reason, the distribution is uniform. To prove that the distribution is normalized to 1, we can compute the integral over all the real line of f of x, but since f of x is 0 outside the interval AB, we can reduce the integral over the interval AB, and since this is a constant, we can put it outside the integral, and what we obtain is this constant times the length of this interval. And what we obtain is the constant 1 divided b minus a times the integral between a and b of dx, but this is exactly b minus a, which shows that the distribution is indeed normalized to 1. The cumulative distribution function of the uniform distribution is given by this formula here, which gives 0 when x is less than or equal to a, 1 when x is greater or equal to b, and this value here, which is a linear value in x, when x belongs to the interval AB. Notice that everything is correct, because if we replace x with a, we obtain a minus a divided by b minus a. The numerator is 0, and so this value is 0. Similarly, when x is b, we have b minus a divided by itself, and so the result is 1. So the cumulative distribution function of the uniform distribution behaves linearly between the extremes a and b with a slope given by 1 divided by b minus a. In this picture, you can see the uniform distribution in the interval 2, 7, and here you can find the corresponding cumulative distribution function. Let's now see what are the expectation value and the variance of the uniform distribution. The expectation value is the average value between a and b, that is b plus a divided by 2, and the variance is b minus a squared divided by 12. Let's see why. The expectation is the integral of x times the density, that is 1 divided by b minus a. This is a constant, and so we can take it out of the integral. The integral of x is x squared divided by 2 that we have to evaluate between b and a. This is the result, and we recognize the fact that b squared minus a squared can be written like b minus a times b plus a. We can erase b minus a, and we remain with a plus b divided by 2. For the variance, we have to compute the integral over a and b of x minus the expectation value that we have just computed, square divided by b minus a. As always, we take the constant out, and then we have to perform a substitution of variable. The substitution is the following. Since here we have a parenthesis square, it would be nice to have this parenthesis as a variable because we can integrate immediately a variable elevated to the square, right? And so we set t equal to x minus b plus a divided by 2. We notice that x is equal to t plus b plus a divided by 2, and the differentials are the same. Why that? Because if we write the differential here, the differential is linear, and so it is the differential of x minus the differential of a constant, but the differential of a constant is 0 because the constant doesn't vary. So the original integral becomes this one here, that we can immediately solve because the primitive of x squared is x cubed divided by 3. You can check that the evaluation of this function in the upper value and in the lower value of integration give rise to this and this. Subtracting, we have this value minus this value, which has a minus sign in front of it, and so it becomes a plus. If we do the math, we obtain exactly b minus a squared divided by 12. The next continuous distribution that we consider is the exponential one. It can be considered a continuous version of the geometric distribution, and as such, it is frequently used to model waiting time before an occurrence. The continuous random variable x is said to follow an exponential distribution with a positive parameter a if its probability density function is given by this formula. That is, 0 if x is negative, and whenever x is non-negative, we have a times the exponential of minus a times x. By integrating, we obtain the cumulative distribution function that is written here. In this figure, you can see the graph of the exponential distribution when we have a equal to 1 in blue and a equal to 3 in red. And on the right, you can see the corresponding cumulative distribution functions. The expectation value of the exponential distribution is given by 1 over a, and the variance is given by 1 over a squared. The computation in this case is a little bit more involved, and so we omit it. The third and final continuous distribution that we consider is the most important one, and it's called normal or Gaussian distribution. The normal distribution has two parameters, usually denoted with mu and sigma square, which appear in the definition of the normal distribution as follows. Let me zoom it. First of all, we notice a constant given by the fraction between 1 and the square root of 2 pi multiplied by sigma. As you can imagine, this constant plays the role of the normalization factor so that the probability is unitary. The functional part of the Gaussian distribution is given by this exponential here, which is the exponential of minus x minus mu square divided by 2 sigma square. It turns out that the expectation value of the Gaussian distribution is exactly mu, and the variance of the Gaussian distribution is exactly sigma square. The Gaussian or normal distribution is called standard when we have a mu equals 0 and sigma equals 1. This function has a bell-shaped graph, which is very famous, and it's depicted in this figure here. As you can see, the maximum of the standard normal distribution is located at x equals 0, but in general, the maximum of the normal distribution is located at x equals mu. Let's see how the normal distribution changes when we change the parameters mu and sigma. The blue and red distributions have the same mu, which is 0, but different sigma. Sigma is 3 for the blue curve and 2 for the red one. This is of course coherent with the fact that sigma is the standard deviation. The green curve represents a normal distribution with mu equals 5 and sigma equals 1. Coherently with what I said before, you have that the maximum of the green curve is located at x equals 5. The last very important information that we have to discuss about the normal distribution is the so-called probability content or mass concentration within 1, 2, or 3 standard deviations from the mean. It's possible to show that the probability content within one standard deviation around the mean is 68%. The probability content within 2 standard deviations around the mean is 95%. And finally, the probability content within 3 standard deviations around the mean is 99.7%. In the great majority of situations, a 2 or 3 standard deviation result, in general we say 2 sigma and 3 sigma respectively, is enough to be sure of the occurrence of a phenomenon. However, it's worth mentioning that in very precise experiments, a 5 sigma result is considered to be the gold standard for significance. The probability content within 5 standard deviations around the mean is so large that it leaves only 1 in a million chance that the findings are a result of random fluctuations. This is, for example, the probability standard accepted by the researchers at the Large Hadron Collider at Geneva in order to accept the discovery of a new elementary particle. When a normal random variable has mean in 0 and unitary standard deviation, we call it standard. It turns out that it's possible to transform a generic normal random variable x into a standard one through a surprisingly simple manipulation. In fact, it's enough to subtract from x the mean mu and divide the result by the standard deviation sigma. The novel random variable x constructed in this way is called standardized, and it follows a standard normal distribution. Sometimes, instead of standardized, you find centered and reduced, where centered is referred to the fact that the mean mu has been set to 0, and reduced means that the variance now is 1. The process is called standardization, and it's useful because many statistical methods and tables are based on the standard normal distribution. Moreover, the standardized random variable z has this very nice and important property that we're going to use in the following example. The property says that for all a between 0 and 1, the probability that z is less than or equal to minus a is equal to 1 minus the probability that z is less than or equal to a. The concrete and very nice example is the following. Suppose that x is a random variable that represents the weight of a newborn. Suppose that you have data supporting the hypothesis that x follows a normal law of mean given by 3.5 kilograms with a standard deviation of 500 grams. Within this model, what's the probability that a newborn has a weight less than 3.1 kilos? The first thing that we do is to standardize the random variable. So mu will be 3,500 grams and sigma will be 500 grams. Then the probability that x is less than or equal to 3.1 kilos can be rewritten like this. This is equal to the new standardized variable. Here we introduce the values of mu and sigma that we have discussed before. And by performing the computation, we have that this probability is exactly this probability here. Using the last property that we have discussed, we can rewrite the probability as 1 minus the probability that z is less than or equal to 0.8. This value can be gathered from the tables of the standard normal distribution or with the help of a computer, and the result is 0.79. So we have that this probability is 1 minus 0.79, which is 0.21, that is 21%.